Okay, so I think we are ready to listen the talk about dynamics of black hole evaporation. Oops, black hole evaporation in a two-dimensional gravity. Please go ahead.
Thank you. Thank you. So let me begin by thanking the organizers for inviting me to this discussion meeting. I was not very clear what I have to contribute to it because there are some things common with turbulence in the sense that I'll be describing the quantum mechanics of open systems which are non-equilibrium. Okay, so I will discuss this work which is now published. It took a long time to do this. You'll see why. And we want to understand the dynamics of black hole evaporation in general, but firstly, model it in 2D gravity, and you'll see how complicated this type of problem is. And it's the work which was done with Advait Gaikwad, Anurag Kaushal, and Gautam Mandal. All right. What is this? Something is funny. The page is not changing. Here, this one. Okay, thank you. All right, so, okay, so I start at 10:15, I think. And so let me first pose the problem to you. What is the problem that we would like to solve? And as you all know, black holes are solutions of Einstein's equations of general relativity, and they exist in nature. And that's an amazing fact, actually, because 20 years ago, when I was talking about black holes, I was just trying to motivate that they may exist. But now they exist. You see them by your naked eyes. So in the presence of quantized matter, black holes are thermodynamic objects, okay? So non-classical effects are very important to make it a thermodynamic object, and they are characterized by mass, entropy, and temperature. And this is the famous Bekenstein-Hawking entropy formula for the entropy of a black hole of mass m, Schwarzschild black hole, which is just characterized by its mass. Okay, so this is a famous result. And what is happening? I'm a little bit confused. Okay. All right. So the temperature of the black hole was calculated in a very famous calculation by Stephen Hawking. And this formula is on his tombstone in England. And so you see this, it's a quantum mechanical effect. Now, the main point here I want to make is that the specific heat of this black hole, if you take this formula and compute this, is negative. So it's a very complicated system, therefore, in the sense that in an asymptotically flat space-time where all these formulas are valid, the black hole is unstable and radiates. And in fact, if you compute the canonical partition function for this type of black hole, it is simply divergent because the entropy grows as the square of the mass, and therefore it overcomes this minus beta m. And it's a very elementary thing, but there is no thermodynamics. This system is not in equilibrium. The partition function doesn't exist. All right. It's a very hard problem to solve, so we move on. Fortunately, in the last 25 years, we have been working on, with ADS spacetimes in the area of string theory, gravity, etc. And the great importance of ADS spacetime is the fact that it forms some sort of a gravitational box, actually. You can't really put a box and have gravitational phenomenon in a standard sense, but ADS spacetime, a hyperbolic spacetime, the gravitational field at the boundary grows. So it's a very natural box. And we can study black hole dynamics in such a box. And I'll just present a very simple formula that the entropy of such black holes goes as mass to some power alpha, where alpha is less than 1. Previously, remember, it was square. And if you compute very elementary, the temperature you can calculate, and it's positive specific heat, and the partition function exists. So there is a very well defined equilibrium statistical physics of black holes in ADS spacetime, unlike in asymptotically flat spacetime. Okay, so this is nice system to work with, which you can compute. And the reason why this black hole is in equilibrium is because when the black hole emits radiation, there's a wall, so it just comes back and reabsorbs it. And that's the somehow physical picture of why this thermodynamics is working correctly. All right. So now, because you have a bath, because you have this boundary wall, such black holes don't evaporate. All right. So in order to study black hole evaporation, you have to extend the system and couple this ADS spacetime to another system, some sort of a bath, or a quantum field theory or whatever, which absorbs this radiation actually. So you can discuss then black hole evaporation in a satisfactory way with this type of open system. Okay. All right, so this is a cartoon, a very simple cartoon of what is this ADS-CFT business. So you have a black hole at a temperature T, and here is the boundary of ADS spacetime, and this blue colored thick line, I have just indicated that there is another quantum field theory which is coupled to this spacetime. And to study black hole evaporation, we need to couple this system at the boundary to this bath. And what we will do in the succeeding minutes that we have is study the case for just d equal to 1. That is, the black hole is in ADS2, okay? And there is a reason why this is also interesting for higher dimensions, because this system, and I will not discuss any of this in detail now, actually descends from a higher dimensional spacetime. So in some sense, we are studying black holes, near extremal black holes in higher dimension. Okay, so what we'll do is we'll study this system by coupling a 1+1 dimensional quantum field theory, just of massless particles, to the SYK model. Okay, the SYK model is a Sachdev E. Kitaev model, which I will explain. And this is the model that we want to study. So this is the duality that I'm talking about, ADS-CFT correspondence, that gravitational phenomena over here interacting with a bath are equivalent or can be calculated equivalently from having some sort of a mechanical model or ordinary quantum field theory coupled to the bath. And this is the place where I will present all our calculations, because we can actually do them. All right. So the SYK model is just sitting at a point. It's a quantum mechanical model. And this is a bath which is made up of NF scale-up fields. Okay. So this is our setup. All right. So what is the SYK model? The SYK model is a model of n fermions interacting in groups of 4. And this is a model studied in condensed matter physics to understand strange metals. So it has n real fermions. These are the anti-commutation relations, and the Hilbert space has dimension 2 to the power of n/2. This is all very simple, actually, for finite n. This is the Hamiltonian with a random interaction, and the interaction is Gaussian, as I've indicated over here. And there's a parameter here which has the dimension of inverse time. Okay. Now, what is known about this? So this model was studied in connection with black holes by Sachdev and Kitaev, and then in a very definitive paper by Stanford and Malosena. And I'm just summarizing some of the results of this series of works, okay? So at large n, in large J, that is low energy, where the frequencies involved are much less than J, these are the results. So there exists an infrared fixed point with an emergent symmetry, and this emergent symmetry is time reparameterization symmetry. And the low energy degrees of freedom are just these one-dimensional maps, actually, from time into some function of time, and this function of time lives on this manifold of diff R1 mod SL2R. These are technical things, but I really have to just very quickly go through them, and please don't mind my, I don't have the time to discuss all this in detail, but we have isolated low energy degrees of freedom as these maps, and there is an effective action of these maps, actually, which is called just, this object is called a Schwarzian in mathematics. And so this is the system that we work with. We have degrees of freedom and a low energy effective action. And there are very important results here. At the density of states of this system is gapless. And because of this exponential of n S naught, where S naught is very specific to this particular model, some number, are very finely spaced levels, which somehow remind you of random matrix theory. And they not only remind you, but they are very deeply related to the spectra of random matrix theory. Now somehow this point over here is not coming. Can you help me actually? So, there are two important things about this model. One is the density of states, and the other one is the 4-point function that grows with time and indicates that this model is chaotic, actually, in the sense that, and it saturates the Lyapunov exponent. So these are the two reasons why the SYK model is very useful to study black hole physics, actually, okay? I'm not able to, I'm not, it's being cut out, huh? Oh, I see, that's what you noticed. Okay, thanks, Samriddhi. All right, I got it. Okay, thanks. Okay, so this is a very important calculation, and this calculation tells you that this 4-point function exponentially grows in a certain range of time, and this is the value of the Lyapunov exponent, which is 2 pi upon beta, which is the max value it can have in some well-behaved quantum mechanical system. Okay, so this is a short summary of the SYK model, and these are the reasons, these 2 points are the reasons why this model has something to do with black hole physics in ADS2. Okay, so let me now move. So now let's look at the other side, the dual gravity in 1 + 1 dimension. So I won't be discussing what these theories are. It's a standard theory of gravity with a scalar field called the dilaton, and there's a metric, and et cetera, et cetera. What are the results of this theory? I mean, the results of interest to me, that it so turns out that the degrees of freedom of this theory are precisely the ones we found in the SYK model. The gravity model is a low energy model, and these are the degrees of freedom, precisely these functions f of t, and the gravitational action actually just a boundary term and reduces again to the integral of the Schwarzian. And these are the parameters from gravity, the value of the dilaton at the boundary, and this is the gravitational coupling, Newton. Okay, so that's amazing that these two systems are described by these maps, and the effective Lagrangian, or the action that describes these degrees of freedom, is nothing but the integral of the Schwarzian over time. Now, of course, you look at the equations of motion of this theory, and you will find that the solution is a very simple solution of tangent hyperbolic. And we had discovered a formula, actually, that if you know f of t, then what is the metric in the bulk? So, okay, this is the formula. So if you look at this classical solution of the gravity or the SYK model, then you essentially find this metric, which is describes a black hole very much like the black hole that Amos was talking about yesterday in ADS2. Okay, so we have this degrees of freedom, we have an action, we looked at the classical equations, we had a solution, and that solution directly maps into black hole spacetime in ADS2. Very nice. Okay, and if you are doing Euclidean, then this is the formula that hyperbolic tangent becomes a trigonometric tangent, and this is the Euclidean black hole solution. Okay, let's move on. So this is in pictures, what's going on. So this is a cartoon of ADS to space-time. The boundaries are time-like, and just given you a diagram of a two-sided eternal black hole, and this is the horizon of the black hole, and this is a solution I mentioned before. And the main point I want to make here is that these boundary degrees of freedom, this f of t's, have a dynamics, right? And here is a solution. Then this is a cartoon of what this solution means. Basically, it means that if this is the black hole solution at temperature T, then this green line is the curve that is parameterized by f and f dot, okay? So this is some technicality, you can plot it. The key point I want to make to you now, and this is a very important point made by Kurkulu and Maldacena, that if this f dot hits a 0, if the Jacobian of the map vanishes, the space-time, the time ends over here, basically. So for this observer, anything that happens outside over here will just go here, and he cannot record it at all. So this is a very beautiful way, a very simple way of characterizing the formation of a horizon. That is the vanishing of the Jacobian of this map T to f of t. Now this type of facility you do not have in higher dimensions. And because of these simple points, we are able to make a lot of progress over here in actually calculating things. Okay, so the key point here is that f dot of 0 signals the appearance of horizon in the bulk geometry. And if f dot is always 0 throughout the history of this particle f of t, then the space-time has no horizon. Okay, so we have some sort of an order parameter now for the formation of a horizon or the non-existence of a horizon. Okay, so this is some general relativity which I just wanted to explain in one slide, and yeah, so here it is. This was all done. All right. Now that we know the degrees of freedom, the Lagrangian for the degrees of freedom, and a bit about the solutions and the notion of the vanishing of the Jacobian of these maps and the appearance of a horizon, I want to get on to the next point, actually, which is also very difficult to do in higher dimensions. What would you say is a candidate black hole state in higher dimensions? It's a very hard problem, actually. But here, in this problem, it's very, very nice and simple that and I'll explain to you now. So this is basically a very important contribution by Kurkulu and Maldacena, that let us look at the spin operators of the SYK model, just 2k minus 1, 2k plus 1, and using the commutation relations or anti-commutation relations of fermions. These are unit operators in the sense the square of S is 1, okay? A very simple point. And we look at eigenstate of this at kth place of the spin. So you essentially look at this state. There is S1 plus or minus 1 here, plus or minus 1 here, plus or minus 1 at the point n upon 2. And if you operate with this operator, you essentially get these eigenvalues. Okay, fine. So this is a basis. The Hilbert space of the SYK model is spanned by these very simple looking states. Of course, but these states are at very high energies. So what you do is you look at the low energy projection of this state by e to the minus L times the SYK Hamiltonian, And this is the temperature, the inverse temperature upon 2. And we assume throughout this work that we are working at very low energies and that there is a good gravity picture in the dual theory. So this is a candidate black hole state, all right? And once I know this, I can do a lot actually. But why is it a candidate black hole state? Why? And this is a theorem actually, which is nothing to do with large n, but at finite n in this model, it so turns out that if you look at the expectation value in this state, the so-called black hole state, of product of operators of the SYK model, which have a special property, which I'll tell you now, then this object on the left-hand side, which is a legitimate expectation value, is nothing but the thermal partition function. The thermal, it's a thermal average actually. And the left-hand side, which is an average, is actually a thermal average. And the temperature is given by inverse of twice L. This is an identity, it's a theorem or whatever. And, but this thermalization formula is valid only for those operators which are flip invariant. Now, flip symmetry is a subgroup of the ON group that is operative here, and it just takes the even fermions to their negatives, and the odd fermions are just left as is. So, okay, so this is the reason why we would like to identify this as a black hole state. Now, you may wonder that if you have a linear space, you know, a Hilbert space is a linear space, so you take a linear combination of those states and then do a low energy projection. Will that be a good black hole state? I'll come back to it at the end actually, but this is one typical state we will work with in the course of this talk. Okay, so this I think is very, very interesting. And one important point I want to make is that this BL state has these spins, right? The important point is that, yeah, no, I think I have said what I had to say. Something else later on. Okay. All right. So this is the flip symmetry, and that's why it's a good state that thermalizes. All these operators instantly thermalize. Now, we come to special operators which violate the spin symmetry. And these operators were introduced by Kurkulu and Mallasena. We just take these spins, these numbers, and multiply them by the corresponding operator. And this is an operator which is not flip invariant, okay? So it doesn't thermalize in some deep sense. That's the point. And now you can do a calculation, which is, you know, elementary but quite long. And you take the expectation value of this operator S, where these numbers S and those in the state are matched. Now, this is the state operator matching, which was introduced by Papadodimos and Subrat Raju. You take such a state, evaluate this operator expectation value, and the answer is to leading order in 1 upon n, the square of the thermal Green's function evaluated at T minus IL. Okay, so this is a statement of a fact, it's a calculation, right? And if you now take the low energy limit of this object, it turns out to be exponential of phi upon 2, where phi upon 2, exponential of phi is defined as f dot. Maybe I forgot to say it somewhere, but this is the definition. Sorry, I perhaps missed doing it in the beginning. Okay. So now we take another operator, which is just the square of, you know, 1. And you can again do the calculation and evaluate it as the 4th power of the thermal Green's function. Very importantly, there's a minus sign over here. So the low energy limit is exponential of minus e. sorry, exponential of phi upon 4 pi. Okay, fine. So we have understood the operator structure of the SYK model. We have understood which operators thermalize and which don't. And it is those operators that don't thermalize we want to essentially probe the black hole with, or in other words, couple these operators to this bath or the conformal field theory, which I will mention next. Okay. All right. So now that we have understood the SYK model in some detail, I want to start doing a computation actually. So, so this is the action of the bath, degrees of freedom, and the bath sort of lives on the positive side of the x-axis. The SYK model is sitting at x equal to 0, and this is the coupling of the bath degrees of freedom to the linear combination of operators of the SYK model. Now, you might wonder why I'm doing it this way, but after a lot of trial and error, we arrived at this particular combination in order to achieve our old. So this problem was a lot of experimental mathematics actually. You try to do things to achieve the result of evaporation. What is it? What are the couplings of the SYK model to the bath which will achieve complete evaporation of a black hole or partial evaporation of a black hole? So I'll come to all that. And so anyway, let's start with this. How we got here is perhaps not important. So there are two control parameters in this problem. This is G and G prime, and in principle, we'll see later, they can also have a certain time dependence actually, okay? So this is our model, and okay. And once again, if you calculate this expectation value, it turns out to be this one, just like before, the way I discussed it with you, that if you have this operator with the same spin values and evaluated as an expectation value with BSL, then you get this simple formula, and so you have your model ready. These are the bath degrees of freedom. These are the SYK degrees of freedom. This is the SYK action, and this is the object that we have written the theory in terms of F dot is equal to e to the phi. And the discussion of going from F to phi was very nicely done by Kamenev and collaborators some time ago. It is not a trivial thing how to sort of understand the measure in the space of maps and relate it to a simple Gaussian measure in phi of t. But it can all be done. This is a like reasonably old subject, so all this is known. So for us now, we have the complete low energy action, the SYK action, the interaction, and the action of the conformal field theory to which the SYK model couples. Now, okay, so now we are done with all our formalism, and now we have to ask ourselves how to do the computation. What do we want to compute? We want to compute essentially the expectation value. We have to compute the density matrix as a function of time, and then evaluate, expectation values of operators, etc. So the basic point is that at time t equal to 0, as we will construct a pure SYK density matrix and a pure state of the conformal field theory, and simply evolve it in this unitary way by e to the minus th, and this is the adjoint action of the unitary group, and it is not the evolution of a simple state, single state, but that is why you have this e to the minus ith and e to the plus ith. Okay, so this is the problem we will try to solve now. Okay, and we always will work in the low energy approximation where the Schwarzschild description is valid, and we can also consider a model where G prime is 0, but that leads to incomplete evaporation of a black hole of a smaller mass, as we will see. Okay, now, so this is our dynamics problem that we have to solve. And okay, so we have to construct these states first, the pure states. So this is the pure density matrix of the SYK model. So this is just this bracket, the BSL state. And we have to construct the conformal field theory pure state, pure density matrix. And it turns out to be just a bracket of a squeeze state over here, which I've just written down, okay? I mean, this is all very elementary quantum field theory, and this is just a wave function of a squeeze state. Okay, so this is what we start with. This is my choice. I give it to you. I now run the dynamics, okay? All right, here. Okay. So we are very careful in our calculation with all our parameters. You know, the parametric range in which our computations are valid are these. So this small l is the inverse temperature of, two small l is the inverse temperature of the black hole. This capital L that occurs in the squeeze state over here acts as the inverse temperature of the bath, and lambda is the ultraviolet cutoff of the conformal field theory, okay? So we have kept all these things, the infrared, ultraviolet cutoffs, and done all our calculations. So you can believe them then. Okay, all right, so now we do the Schwinger-Keldysh. I think Loganayagam talked about it, but there were no formulas, but you know, I cannot give a talk without formulas. So this is the Schwinger-Keldysh. So how do you now compute the density matrix evolution of a open system, of a system, the SYK model coupled to a bath? So this is a standard Keldysh formulation of the problem. Because the density matrix is evolved from the left and right by two operators which are inverse of each other, you essentially have a contour that goes like this. So you have to double the degrees of freedom in order to evaluate this type of density matrix in the path integral. So the Feynman path integral is written on these contours, actually. I can't go into details, but this is where we are. And now what we do is we integrate out the path degrees of freedom, and we get this Feynman-Vernon influence function. How much? 3 minutes. Oh my God. But I think I started a bit late.
No, this started when you started.
All right.
Then you have a few minutes for the questions. So you can...
Okay, but I haven't even reached. All right. I had to explain all these things to you, otherwise you wouldn't follow what I'm doing. So anyway, I'll manage. Few minutes more you'll give me. Yeah. Thank you. All right. So this is the. I'll go now at very fast, right? So you integrate out the path degrees of freedom. This is the influence functional, and so you have an effective action. And once you have an effective action, you start computing actually. So you do the Keldysh trick of doing these rotations. They're called Keldysh rotations. And this is all textbook material. In Kamenev's book on this subject, everything is written more or less. So I'm not doing anything very original, but we are applying it to this interesting problem. So what we have now essentially is to compute this in 1/n expansion. So I sort of expand the action and keep the leading terms, the Gaussian terms in the fluctuation delta phi q. And essentially, I have this type of path integral to talk about. Exponential of the integral is over delta phi q. And so you have essentially a kernel, which is quite complicated and non-local in time, but we can deal with all that. And ultimately, what you do is introduce these noise variables, because you have this Gaussian, and introduce the noise variables and put it in the path integral, and you arrive at this stochastic differential equation to solve. So this is the problem we have to solve now, this stochastic differential equation with this type of memory term, and the noise is colored noise, and the kernel over here is given by this. So this is the mathematical problem that we have to solve. Now this is not a trivial problem, and most of the references to people who deal with this type of problems are in financial mathematics. It's a very interesting fact I found. Okay, so let's try to solve this problem. You break it up into, so the second order equations can be made into local third order equations whose solutions are also well defined. And we try to solve this problem in terms of the full equation, stochastic equation, in terms of a classical equation, and around it a fluctuation like this, okay? So you do this, and this is the space of solutions for the control parameters G and G prime, and you find essentially that outside this dashed line, the solution doesn't exist and it blows up. And these are the red colored dots over here are solutions which correspond to asymptotically small black holes, and this green one corresponds to complete evaporation, okay? So this can be done, and these are the numerical solutions that confirm this plot, and okay, so, and this is an example of a solution that blows up, and the solutions blow up because the back reaction of the bath increases actually, and your entire formalism of the SYK model really breaks down. So, okay, now this is a solution in the red region. So you can actually see that the solution goes asymptotically in time, like minus A times some time t, and this parameter A is related to the inverse temperature of a small black hole. So these are small black holes, means black holes at lower temperature, which are the asymptotic state, okay? And this G star over here is nothing but this 2 pi upon beta J. Now, let's go to the solution in the green region. So this is where the real complicated problem is. So you find that the solution in the green region around this point phi EQ, which corresponds to setting the coefficient of the integral in the integral equation equal to 0, is a highly oscillatory solution, okay? And you can analyze it using Airy functions, whatever. And the problem is that you have a harmonic oscillator in a time-dependent potential. As the time grows, the frequency square grows, and our low energy approximation breaks down. So you would want to essentially restrict the time which you use to run this routines to calculate these solutions to some maximum time, which is given by this type of formula. So you have to restrict the time. But then what do you do for the asymptotic physics? What you do is you introduce a quench. And this is where a certain quench is introduced by us in the space of these control parameters, and it dies, the bath is decoupled as it is pumping energy into the black hole region in this very specific way, as 1 upon square root of t dies as 1 upon square root of t. And now you can redo the entire analysis of this problem, and you have this equation, and the frequency is also stabilized, and all these things you can write down. The most important point over here in this solution is that F dot is given by this formula is always positive. So that is complete evaporation. Okay, so let me just move on quickly. We can calculate how the evaporation goes and how the energy is dissipated. And this is the geometrical picture. What corresponds to the red region is this one, where you have a smaller black hole over here, and this corresponds to complete evaporation, okay? All right, so we can have a very nice correspondence between complete evaporation and the geometry, or partial evaporation and the geometry. And the very important point in this whole thing is that you have a solution, you know, the end point of evaporation is a very, very oscillatory one, okay? So let me just, you're a very tough chairman.
Yeah, I know.
I'm also very tough. Wait, just give me 1 or 2 minutes, okay? Okay, so now we compute the fluctuation equation, the fluctuations in this background, which we calculated. And in the case of the red region of partial evaporation, you essentially get a formula for the two-point correlation like this, and you essentially infer a diffusion constant, which is consistent with the Einstein relation, Einstein's Moriconi. Okay. However, if we do the same fluctuation calculation for the two-point function around this oscillations, you essentially get this formula. And the important point here is that the diffusion constant is in this case of the complete evaporation, the diffusion constant is not linear in the inverse powers of L. Okay, as we can see just numerically from over here. So in summary, the end point of evaporation of a black hole is a very complicated phenomena, even in this very simple model of very large fluctuations. And we can compute in this simple model all these things very precisely. And here is a summary. And mind you, I have been working with a unitary theory in the sense that I evolved a unitary density matrix in time coupled to an open system and got all these results. So in a sense, there is no information loss in this problem at all. Okay. So we have demonstrated the dynamics of black hole evaporation or dissipation in the SYK model coupled to gravity. And this is the SYK model. I won't repeat what it is. And calculation is done in this very low energy approximation using the Schwarzschild mode that describes the geometry in the dual JT gravity. Okay. And there are some future questions, which...
You can leave it for the discussion, maybe.
Okay.
What do you think? Thank you very much.
Yes,
thank you very much. You have used all your questions time and some of our tea break time, but I will allow some questions anyhow. So
thank you so
please,
much.
if there are questions or remarks, please.
Yeah.
So very nice presentation. I have one question. I mean, when you look at condensed matter physics and you ask coupling a system to a heat bath, very often, I mean, you would not couple it to an extra quantum field, but you just replace this somewhat phenomenologically, but extremely successful by Lindbladian operators. So this is.
I couldn't actually get
you replace the quantum field by Lindbladians. I mean, when you look in condensed matter physics, this is how people model actually a heat bath.
Yes.
And so I just wonder whether instead of coupling it to a quantum field, which is write down the corresponding Lindbladians and analyze these kind of dissipative equations. And so my question is, did you ever try to use Lindbladians in your context?
No, not the Lindblad formulation actually. But you may wonder why these operators have to be so special. So this we haven't understood, because if you want to study evaporation, you just have to touch two systems. But in this case, we found that if you just use any operator actually of the SYK model to couple to the bath, it doesn't do the job basically of complete evaporation. For example, yeah.
One more question. Yeah. So in the first slide, you showed that the system is unstable. Then you went to reconstruct some way that you make it stable and so on. But in turbulence, we deal with unstable systems. So we don't really worry about, so we do the dynamics without worrying about heat bath. And would you like to comment? Is it possible to do that kind of calculation, just do dynamically?
I mean, I really don't know how to formulate the evaporation problem of a Schwarzschild black hole actually. So this is why I was studying black holes in ADS spacetime, not asymptotically. Maybe somebody has a, Luca, you have something to say on this? So.
No problem. It's just a wild thought.
No, yeah, that's a very hard problem to solve actually. Yeah. Okay.
Other questions? If not, let us thank both speakers of this morning. We have the tea break. Thank you.